welcome to this problem walkthrough. Today, we'll explore an interesting problem from LeetCode, number 1920, build array from permutation. This problem challenges us to construct a new array based on specific relationships between the indices and values of an input array. Let's dive in and understand how to approach this step by step. In this problem, we are given a zero-based permutation array called nums. This means that the array nums is of size n and contains all the integers from 0 to n1, each appearing exactly once. Our task is to build a new array ans of the same size, where each element at index I is determined by looking up the value at nums I. Formally, for any index I within the range 0 to n1, ans I is equal to nums I. This process uses the values in the nums array to define the indices for creating the new array. Once this transformation is complete, we return the resulting array ans as the output. The input to the problem is the array nums, and the output is the transformed array ans. Let's look at the first example to understand this process. Suppose nums is 0, 2, 1, 5, 3, 4. The output for this input will be 0, 1, 2, 4, 5, 3. Here's how it works step by step. For I equals 0, we calculate ans 0 as nums 0, which evaluates to nums 0, and that is 0. For I equals 1, ans 1 is nums 1, which becomes nums 2, and that is 1. Similarly, for I equals 2, ans 2 is nums 2, which leads to nums 1, and that is 2. By continuing this process for all indices, we eventually get the output array 0, 1, 2, 4, 5, 3. This example demonstrates how each value in ans is derived by accessing the array nums twice. Now, consider the second example where nums is 5, 0, 1, 2, 3, 4. The resulting array ans will be 4, 5, 0, 1, 2, 3. Let's break it down. For I equals 0, ans 0 is nums 0, which evaluates to nums 5, and that is 4. For I equals 1, ans 1 is nums 1, which becomes nums 0, and that is 5. For I equals 2, ans 2 is nums 2, giving us nums 1, and that is 0. Continuing in this way for all indices, we construct the output array 4, 5, 0, 1, 2, 3. This demonstrates that the transformation works consistently, even when the values in nums are not in ascending order. Next, let's look at the third example where nums is 3, 1, 2, 0. The output for this input is 0, 1, 2, 3. For I equals 0, ans 0 is nums 0, which evaluates to nums 3, and that is 0. For I equals 1, ans 1 is nums 1, which leads to nums 1, and that is 1. For I equals 2, ans 2 is nums 2, giving us nums 2, and that is 2. Finally, for I equals 3, ans 3 is nums 3, which evaluates to nums 0, and that is 3. This gives the final array 0, 1, 2, 3. The example highlights how the approach works regardless of the order of elements in nums, as long as the array satisfies the zero-based permutation condition. Finally, let's consider some edge cases. First, if the input array nums has only one element, i.e., when n equals 1, the array will always be 0, and the output ans will be identical to nums. For example, if nums equals 0, the output is ans equals 0. On the other hand, if nums is in descending order, meaning it starts from n1 and goes down to 0, the output will reflect a reverse mapping. For instance, if nums equals 4, 3, 2, 1, 0, the output will be 0, 1, 2, 3, 4. These examples illustrate the importance of handling different input patterns while adhering to the constraints, such as the distinctness of elements and the size limits for n. To start, let's consider the brute force approach. The intuition here is straightforward. We need to build a new array, ans, where each element is determined by the relationship ans I equals nums I. This means we directly follow the problem statement by calculating the value for each index step by step. The steps are simple. First, we initialize an empty array ans of the same size as the input array nums. Then, we loop through all the indices from 0 to n1. At each index, we compute the value for ans I, by substituting nums, I, into the array and retrieving the corresponding value. Once all indices are processed, we return the newly constructed array ANS. Now, in terms of complexity, the time complexity is O, n, since we perform a single loop through the array, and the space complexity is also O, n, due to the additional memory used for the output array. While this approach is very simple and clear, it relies on extra space, which can be a drawback if memory usage is a concern. However, this trade-off is acceptable in most cases because the memory overhead is minimal and the logic remains easy to understand. Now, let's explore an alternative method called the in-place transformation approach. The key idea here is to avoid using extra space by modifying the input array nums directly. To achieve this, we encode both the original value and the desired new value into each element of the array. This is possible because the input array is a permutation of integers from 0 to n1, meaning all values are within this range. Using modular arithmetic, we can retrieve both the original and new values from a single element. Specifically, we use nums I%n to extract the original value and nums I /n to access the new value. The process involves two main steps. First, during the encoding phase, for each index I, we update nums I by adding the new value, which is nums I%n multiplied by n. This ensures the new value is stored without losing the original value. Then, in the decoding phase, we retrieve the new values by dividing every element by n. This approach maintains the O, n, time complexity because we iterate through the array twice, and it reduces space complexity to O1, since no additional memory is required. However, this method modifies the input array, which might not always be acceptable depending on the context. There are trade-offs to consider with the in-place transformation approach. While it is highly space efficient, it introduces additional complexity due to the use of modular arithmetic. It also modifies the original input array, which could be problematic if the data needs to be preserved for other operations. With this in mind, we opted for the brute force approach as our chosen strategy. The main reason is its simplicity and clarity. Since the problem constraints allow for an additional memory allocation of O, n, the extra space usage is negligible for arrays of size up to 10,000. Both approaches achieve the optimal time complexity of O, n, but the brute force method avoids potential pitfalls associated with modular arithmetic and directly aligns with the problem's requirements. The key insight is that the input array being a valid permutation ensures all indices are valid, making both solutions safe and efficient. By prioritizing readability and maintainability, the brute force approach strikes a good balance between simplicity and performance. However, if memory usage were a critical concern, the in-place transformation would still remain a viable alternative for solving this problem. To solve this problem, the goal is to construct an array called ANS such that each element at index I in the array is determined by the value at nums I. The input array nums has a size of n, and we are given that all its elements are valid indices within the range of 0 to n1. To begin, we ensure that the input is valid. This involves checking that the array is not empty and confirming that all elements in nums fall within the specified range of indices. Next, we initialize an empty result array ANS with the same size as nums. This will store our final values. Since we will overwrite all initial values, placeholders like zeros can be used during initialization. After this, we iterate through every index I in nums. For each index, we first fetch the value nums I, which we can call x. Then, we access the value at nums x and assign this value to ANS I. This ensures that we map the elements correctly based on the problem requirements. Once we complete the loop, the result array ANS will be fully populated, and we return it as the output. To see the process more clearly, let's examine an example where nums equals 2, 0, 1. First, we initialize the result array as ANS equals 0, 0, 0. Now, during the first iteration, where I equals 0, we see that nums 0 equals 2. From there, we look up nums 2, which equals 1. So, we update ANS 0 to 1. After this step, the result array becomes ANS equals 1, 0, 0. Next, for the second iteration where I equals 1, we find that nums 1 equals 0, and looking up nums 0 gives us 2. We then assign this value to ANS 1, making the result array ANS equals 1, 2, 0 at this stage. In the final iteration, when I equals 2, we observe that nums 2 equals 1. Using this value, we access nums 1, which equals 0. We assign this value to ans2, resulting in the final array ans equals 1, 2, 0. With all iterations complete, we now have the output ans equals 1, 2, 0. This step-by-step approach demonstrates how we can systematically build the result array by following the given mapping rules. This approach brings to light some important insights about the algorithm. First, the problem is fundamentally about direct mapping, where each element in the output array is derived through two lookups in the input array. By iterating through the input array once and performing two constant time operations for each index, we adhere to the problem constraints while keeping the computation efficient. In terms of time complexity, the algorithm involves a single loop over the array of size n, with constant time operations for each iteration. This results in an overall time complexity of O(n). Regarding space complexity, the only additional space we use is for the result array ans, which has the same size as the input array. Thus, the space complexity is O(n). The algorithm primarily relies on two data structures. The input array nums serves as a source of the initial mapping. It is accessed twice during each iteration, once to fetch the value at index I and another time to fetch the value at nums I. The result array ans is the second data structure, which stores the final output. This array is updated index by index as we progress through the loop, and it ultimately holds the desired permutation based on the problem's requirements. Finally, let's consider some edge cases to ensure the algorithm handles all scenarios correctly. If the input array nums is empty, the output should naturally be an empty array as well. For an array with a single element, such as 0, the output will also be 0, since nums 0, simply evaluates to nums 0. For large arrays, such as when n equals 10⁻⁴, it's important to ensure that the algorithm executes efficiently without exceeding memory or time constraints. By adhering to the O(n) time and space complexities, this approach is well suited for handling even the maximum constraints effectively. This Python implementation begins by defining a class solution with a method build array that takes a single argument, nums, which is the input list. The problem requires constructing a new array ans such that each element in ans corresponds to the value found at the index specified by nums I in the original list nums. The solution starts by initializing an empty list ans, which will serve as the result array. It then iterates through the indices of the input list using a for loop. For each index I, the code computes the value nums I, and appends it to the ans list. This computation effectively maps the index I to its derived value using the permutation logic described in the problem statement. Finally, the method returns the constructed list ans as the output. This approach works efficiently with a time complexity of O(n), where n is the size of the input list nums, and it uses O(n) additional space for storing the result. The implementation is clean and adheres to the constraints provided in the problem. This is the Java implementation of LeetCode problem number 1920, build array from permutation. The logic mirrors the provided Python solution. The method buildArray accepts an integer array nums and constructs a new array where each element at index I is set to nums I. Java-specific differences include the use of type declarations, e.g., int, for arrays, and array initialization with new. The solution maintains clarity and mirrors the Python approach exactly. To begin, we are given the input array nums as 0, 2, 1, 5, 3, 4. We initialize an empty list called ans, which will store the resulting array. Starting the iteration, at index I equals 0, the value of nums I is 0. Using this, we calculate nums I, which resolves to nums 0 equals 0. This value is appended to ans, so now ans equals 0. Next, at index I equals 1, the value of nums I is 2. Computing nums I gives nums 2 equals 1. This result is appended to ans, updating it to 0, 1. Continuing with the iteration, at index I equals 2, the value of nums I is 1. We calculate nums I, which results in nums 1 equals 2. Appending this to ans gives us 0, 1, 2. Moving to index I equals 3, where nums I is 5, we compute nums I equals nums 5 equals 4. Adding this value to ANS updates it to 0, 1, 2, 4. At index I equals 4, nums I is 3. Calculating nums I gives nums 3 equals 5. Appending this value results in ANS equals 0, 1, 2, 4, 5. Lastly, at index I equals 5, nums I is 4. Computing nums I gives nums 4 equals 3. Adding this value to ANS completes the array as 0, 1, 2, 4, 5, 3. With all iterations complete, the final output for this example is 0, 1, 2, 4, 5, 3. Moving to the second example, the input array is now 5, 0, 1, 2, 3, 4. Once again, we initialize an empty list ANS to store the result. Starting at index I equals 0, nums I is 5. We calculate nums I, which gives nums 5 equals 4. Appending this value, we start with ANS equals 4. At index I equals 1, nums I is 0. Calculating nums I gives nums 0 equals 5. Adding this value updates ANS to 4, 5. For index I equals 2, nums I is 1. Computing nums I results in nums 1 equals 0. Appending this value makes ANS equals 4, 5, 0. At index I equals 3, nums I is 2. We calculate nums I equals nums 2 equals 1. Adding this value updates ANS to 4, 5, 0, 1. Finally, at index I equals 4, where nums I is 3, we compute nums I equals nums 3 equals 2. Adding this value gives ANS equals 4, 5, 0, 1, 2. At index I equals 5, nums I is 4. Computing nums I gives nums 4 equals 3. This value is added to ANS, resulting in 4, 5, 0, 1, 2, 3. The final output for this example is therefore 4, 5, 0, 1, 2, 3. Now, for the third example, the input array is 1, 0. As before, we initialize ANS as an empty list. For the first index, I equals 0, nums I is 1. Calculating nums I equals nums 1 equals 0, we append this value to ANS, starting with 0. For the second index, I equals 1, nums I is 0. Computing nums I gives nums 0 equals 1. Adding this value updates ANS to 0, 1. With no more elements to process, the final output for this example is 0, 1. Summing up the approach, for each index I, we calculate the value of nums I, and append it to ANS. This algorithm iterates through the input array once, achieving a time complexity of O(n). The space complexity is also O(n), as we store the result in the output array ANS. To analyze the time and space complexity of this solution, let's start with time complexity. The algorithm uses a single for loop that iterates over every index in the input array nums. For each iteration, the operation nums I is performed. Since arrays allow random access, retrieving nums I is an O(1) operation. Similarly, nums I involves two constant time operations, first accessing nums I, then using that value as an index to access another element in the array. This means each iteration of the loop takes constant time, or O(1). Since the loop runs n times, once for each element in the array, the total time complexity is O(n). Now, for space complexity, the solution uses an additional list ANS to store the result, which has the same size as the input array nums, containing n elements. Beyond this, no other data structures are used, and operations like accessing elements of nums occur in constant space. So, the total space complexity is determined by the result array ANS, which is O(n). When looking at the best, average, and worst-case performance of this algorithm, there is no variation based on the input. This is because the algorithm always processes the entire array, performing the same constant time operations for each element. Therefore, the time complexity remains O(n) in all cases best, average, and worst. Similarly, the space complexity is always O, n, as the result array must store all n elements. Now, let's consider how this optimized solution compares to a naive approach. In a naive implementation, instead of directly indexing into nums, we might use nested loops to construct the result array. For example, we could iterate through each index I of nums, and for each value, perform a linear search to find the corresponding element. This would involve iterating through the array again for every index I, resulting in a significant increase in runtime. With the naive approach, the use of a nested loop means that for each element I, a linear search is performed to find nums I. This inner loop runs O, n, times for each of the n elements, leading to an overall time complexity of O, n squared. However, the space complexity remains O, n, since the result array ANS is still required. In contrast, the optimized solution avoids nested loops by directly accessing elements using array indexing. This reduces the time complexity to O, n, as the single loop iterates through the array once, performing constant time operations during each iteration. The space complexity also remains O, n, as only the result array ANS is used. To mathematically verify the big O analysis, note that the algorithm performs n iterations, with each iteration taking constant time. This gives a total time of n asterisk O, 1, or O, n. Similarly, the space required for the result array of size n confirms a space complexity of O, n. This makes the solution optimal for both time and space efficiency in this problem. When solving this problem, there are several common mistakes to watch out for. First, be cautious about accessing out-of-bound indices. For example, when working with expressions like nums I, you must ensure that all indices are valid, otherwise, you risk runtime errors. Always double-check the constraints and the input size to avoid these issues. Next, it's critical to handle edge cases properly. Scenarios like empty arrays, arrays with only one element, or arrays with repeated elements are easy to overlook but can lead to incorrect results if not tested. Another mistake is modifying the input array directly when the problem requires building a new output array. Unless the problem explicitly allows in-place modifications, altering nums can cause logic errors in subsequent computations. Additionally, overlooking time complexity is a frequent pitfall. While a brute force solution might work for smaller inputs, it is unlikely to handle larger test cases efficiently due to time limits. Aim for optimized solutions after evaluating the constraints. Finally, misunderstanding the problem requirements can lead to errors. For example, in constructing ANS I equals nums I, you need to carefully follow the order of operations, first fetch nums I, and then use it as an index. Misinterpreting this can derail your approach entirely. In interviews, solving problems like this involves more than just coding. It's important to recognize patterns, as many problems involving array transformations depend on identifying relationships between indices and values. Pay close attention to how these interactions shape the solution. Constraints-driven optimization is another key factor. For instance, if the problem specifies n up to 10 to the power of 4, brute force solutions are unlikely to pass due to time limits. You should prioritize O, n solutions, often achieved using a single traversal or leveraging extra space. Speaking of space, understanding the trade-off between time and space is crucial. For example, creating a new array may simplify the logic but increases space usage, while in-place modifications save space but may not always be permissible. Interviewers also value thoroughness, so discussing edge cases such as empty arrays, arrays with maximum input sizes, or other boundary conditions can leave a strong impression. Lastly, testing your solution is vital. Simple test cases, like nums equals 0, 2, 1, 5, 3, 4, are excellent for verifying basic logic, while edge cases like nums equals 0 ensure the smallest inputs are handled gracefully. This problem shares similarities with several other popular LeetCode challenges. For instance, LeetCode 1920, which we're discussing, involves constructing ANS I equals nums I. Another example is LeetCode 238, product of array except self, which focuses on array manipulation under specific space constraints. LeetCode 448, find all numbers disappeared in an array, is another related problem that emphasizes indexing and modifying the input array. Similarly, LeetCode 442, find all duplicates in an array, involves array transformations and in-place modifications. These related problems provide excellent opportunities to practice array manipulation techniques. When it comes to approaches, the brute force method is a straightforward option to begin with. It operates with a time complexity of O(n) squared and a space complexity of O(1), making it easy to implement. However, this approach becomes inefficient for larger inputs, as it will likely exceed time limits. While brute force has its place as a starting point, it is not ideal for scaling to large test cases. An optimized approach that uses extra space offers a significant improvement over brute force. By creating a new array to store the results, you can achieve a time complexity of O(n) and a space complexity of O(n). This method is faster and ensures clarity in logic, but it does require additional memory, which might be a consideration in environments where space is limited. On the other hand, an optimized in-place approach modifies the input array directly, resulting in both time and space complexities of O(n) and O(1), respectively. This is ideal when space savings are critical, but it may not be acceptable if the problem explicitly disallows input modification. Each approach has its own trade-offs, and demonstrating an understanding of these during interviews showcases your ability to evaluate problem-solving strategies thoughtfully. Discussing these alternatives also highlights your flexibility and depth of knowledge in tackling algorithmic challenges. Great job completing this problem. In summary, we tackled the challenge of building an array from permutations by understanding the relationships between indices and values. Remember to always analyze edge cases and aim for optimized solutions. If you found this helpful, feel free to like, share, and subscribe to stay updated with more problem walkthroughs. See you in the next one. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!